Hello and welcome to part 2 of my tutorial on using Julia to run economic simulations. You should watch part 1 before watching this video. It provides some important context. So in part 2, we're talking about how to find the equilibrium given the market that we've set up. And what equilibrium means in the case of this exchange economy is that no trader has an incentive to change her price. So the equilibrium is a vector of prices P that satisfies these two conditions. First, the demand for each trader has to be less than or equal to the quantity or the supply that she has on hand. And additionally, if this is going to be a strong inequality, that is, if the demand is going to be truly less than the supply, we're only going to let that happen. We're only going to let the trader settle for this low demand if she has already decreased her price all the way to zero. The kind of informal way of thinking about this is that for most traders, we want the demand to equal the quantity, and we'll make an exception if there's a good that's just so unattractive that even when its price is zero, that there's no way for it to sell out. Under some technical conditions on the demand function, which we created above, and on how the traders update their prices in response to excess supply or demand, we can show that a tâtonnement process, which you'll recall is the price update rule defined above, converges to an equilibrium. So to find that equilibrium here, we are going to use a special kind of tâtonnement process, which is called the simultaneous tâtonnement process. And here I've gone ahead and coded in the simultaneous tâtonnement process's price update rule. And that looks like this. The first thing we're going to do is take in a vector of prices P, and the goal is to return the updated prices that will hopefully be closer to the equilibrium. What we do is we measure the demand at these prices, and then we subtract the quantity on hand to get what we can call the excess demand. Recall that this is a vector. So here we have a vector of excess demands, and if at a certain index, for a certain trader, the demand exceeded the quantity, then that trader actually had excess demand, and she is going to want to increase her price. So when this is positive, the price will increase, and that makes sense because there was more demand than the trader wanted. On the other hand, if this quantity is negative, then we have excess supply, and we're going to be adding a negative number, so P is going to get smaller. Now, there's a little bit of decoration on this price update. The first thing you'll notice is this parameter alpha, which describes essentially how reactive the traders are. If A is very large, then when a given trader sees extremely high demand, or rather when a given trader sees any level of excess demand, then the trader is going to increase her price by a lot, right? So she's very reactive or very aggressive. Whereas if alpha is small, then if there's some excess demands, the trader doesn't want to rock the boat, right? So she's just going to increase her price slightly. This alpha parameter is very important theoretically, because if you read the proof that shows that this tâtonnement process converges, it requires that alpha not be too large. Alpha needs to be small. The second thing you'll notice is this max function, and the dot means that this max is working on a vector, and it's working entry-wise. So what this means is that for all of these updated prices we calculated here, if there is a certain price that had so much excess supply that the price update pushed it to a negative number, we're going to instead just set the price to zero. So we agreed earlier that we would not allow negative prices, and so we are using this max function to just clamp all of the prices to be positive or non-negative in case that scenario comes up. The other thing we need to do is normalize the prices to add up to 1. And the theoretical reason that we can do this is that if we start with a vector of prices that adds to 1, and the result ends up adding to something that's different than 1, then even if we change the result by multiplying or dividing by a positive scalar, the demand at the new prices does not change. We assumed earlier that the demand function is homogeneous in P. So when I take this res and I multiply it by a scalar, its demand does not change. However, you might notice that this seems to violate our assumption that each of the traders acts on her own, right? And says, I'm going to increase my price now, or I'm going to decrease my price now. Instead, this equation, this statement seems to imply that the traders can get together and collude and say, we're going to make sure all of our prices sum up to 1. So this poses a bit of a theoretical challenge, but there are a couple ways to argue that it is okay. The first is what I just mentioned. Because of homogeneity, we can think of the resultant price vector as not tired. The next thing that this price update function does is it divides the updated prices by their sum. And what this does is it ensures that the prices sum to 1 at all times. And we know from our homogeneity assumption on the demand function that if I divide the prices by a scalar, a positive scalar, which this is, then it will not change the demand at all. So you might think that asking to divide the prices by their sum somehow violates our assumption that the traders are acting alone because it requires them to sort of collude and figure out what the sum of their prices is. But in actuality, we can think of this as not changing the prices, but simply changing the unit that we use to measure the prices. And even if you leave out this line, what you will see is that instead of the prices converging to some parallel lines or to some fixed p-value, instead the prices will sort of gradually inflate in value. However, the important thing is that the ratios among the prices will still be constant. So it will be an equilibrium with respect to the homogeneity assumption. In this case, we're just taking care of that assumption at the outset. Another way to think about this is actually the only reason this price normalization step is necessary is because of this max in here. If we look very closely at this price update calculation, and we imagine how it affects the sum of the prices, well, if P itself already sums to 1, and I took the sum of these updated prices, then the sum of the first term is going to be 1. The sum of the demand we know is always 1 by our Walrasian assumption. And likewise, the sum of the supply is also 1. So this part in parentheses is going to be 0 always when we sum across all of the goods. And therefore, this price update does not change the total sum of the prices at all. That's because the sum operation is a linear operator. Unfortunately, the max operator is not linear. So because we have stipulated that prices cannot be negative, we have broken that lovely property. And something to think about is if in your application or the situation that you want to model, there is actually a meaningful interpretation of negative prices, then you can go ahead and take out this max and take out the normalization step and see what happens. So that's a theoretical angle that I will leave it to you to explore. So we have created our price update rule, and now let's just test out that it's working by creating some current prices. We're going to normalize these at the outset to sum to 1, and we're going to make, again, our sort of data frame to see what's going on here. So let's pick any trader. I'm going to look at trader 3. Her current price is 0.129, and she observed a demand that was much lower than her supply. So what she's going to want to do is lower her price, probably quite drastically, and sure enough, we see that her new price is about 2/3 as large as her original price. If we look at another trader, like say trader 5, her price was 0.18. She received excess demand, so she's going to want to increase her price. And sure enough, we can see that our price update rule has moved her price in the correct direction. So on some level, it seems like we have a realistic model of how the traders would react to having observed their demand at these current prices given on the left. However, what we want to do is not just calculate one price update, but what we actually want to know is how will the prices change over many iterations of this process. And each iteration would be one market cycle. It could be a year, it could be a day, it depends on the context. And the other thing we'll notice is that this price update rule does not require the traders to know the shape of their demand curve. It doesn't require them to know the matrix A that we use to build this demand function. All they have to do is observe one data point, right? Which is the demand for their good at their current price. They don't need to know any of this, any of that, or any of the details of demand. So what I've created here is a price path function. And what this function is going to do is it's going to repeat the price update a bunch of times and show us how the prices for the goods in our market sort of evolve over time. I start by initializing my price container. And in Julia, an empty vector is notated just like this with a pair of square brackets. And if I want to, I can annotate my empty container on the left with the kind of object that I want to put in it. So in this case, I've said that I'm creating an empty vector. And what kind of vector is it? It's a vector of vector float64. So this is a vector of vectors that I've initialized here. And over here, I've said that its contents are float64. So this can be kind of confusing because you only see the word vector once, but it's actually a vector of vectors is what we're going to end up with. And if I just wanted a vector of float64s, then what I would do is I would actually completely remove this, and this would be a blank vector of float64s. But because our prices are vectors, we need a vector of vectors. Then for each time period in however many I said I wanted to calculate, I think we'll do 50, I'm going to push my current prices. So you can think of this as appending them to the price container. I'm going to put my current prices there. Then I'm going to calculate the updated prices. And then I'm going to keep repeating that. So what our price container should be is a vector of vectors, a list of lists in essence, of the price vectors at each point after over 50 iterations of this process. So I'm going to go ahead and calculate an initial price, which is just completely randomly generated. And then we're going to do 50 iterations of this tâtonnement price update. And we're going to see what kinds of prices we end up with. Here I've just shown you the first 5 elements of the price container vector, but as you can see, each essentially column here corresponds to one good. So here is a good that was overpriced, right, and it appears to be decreasing in price over time, whereas here's one that increased a little bit and then went down. So we can see all sorts of dynamics emerging here. And a really great way to visualize this would be to plot the price paths of all of our goods. So time is moving from left to right, and we can see that we started at some random prices, and they all sort of crisscrossed over each other. And after about, say, 15 iterations, we reached a very solid, stable equilibrium. So this suggests that the tâtonnement process has converged to an equilibrium. And here I'd like to just kind of show off a cool Julia trick here. I'm going to take my same exact plotting code here, but I'm going to change it so that it only shows the first t prices. So depending on what this lowercase t refers to, it could be the first 5 prices or the first 10 prices, right? It's kind of scanning from left to right here. So I'm going to make that partial plot. I'm going to ensure that it's showing, though, the full range of t values that I'm interested in. And all I have to do is put that plotting code inside a for loop that varies over t, which is which price point I want to show up to. And I can use this animate macro to create an animated GIF that will show exactly how these prices develop over time. So I've stored that in the anim object. And if I go ahead and call this, it should create a nice animation that looks pretty similar to this graph up here. And it will by default also save the GIF file to my current working directory. So that turned out pretty nice, right? And this is a really cool feature you can use in Julia. I would say compared to Python, it's a lot easier to create these kinds of animations. Of course, it's doable in Matplotlib, but it takes a little bit more careful syntax. So here what we've done is a simulation, right? We're looking at how do the prices move over time and can I kind of draw their path? But another thing we might want to do is just find those equilibrium prices, right? So I might only care about this value over here on the right, and I don't really care what path it took to get there. So in this case, we can actually make a much more efficient, much more performant code by, instead of storing the intermittent values of the prices as they're updated, we can instead simply overwrite P with its price update, and then return that after repeating that update over a large number of iterations. So essentially what I'm trying to do is I take P, and then I do a price update of it, and then I do a price update of that, and then I do a price update of that. I want to do this 100 times and see what we get to, and we're going to hope that eventually this converges. So here, that happened pretty quickly, right? I did 100 iterations of this price update calculation, and I got a price that I am claiming is the equilibrium price for this market. But how do we know if we got it right? Well, one way to check is we can see if the price update step corresponding to this new price is the same, right? If the optimal response or for each of the players to this current price is the same, then we know that no matter how many additional price updates I tack on, it's never going to change. That suggests that no player has an incentive to change their response, and therefore that we have reached the equilibrium. So we're going to check now that P bar is equal to its price update, and indeed we got true. I put an approximately equal here because even after 100 iterations, you can occasionally get very small changes on the last digits. We can actually make this equilibrium calculator go even shorter, that is in terms of the text representation of the code, using a kind of special Julia trick that's called function composition. To explain this trick, we need to get a little bit into how Julia works. So if we think about the plus operator, this is what's called an infix operator. So that means it acts on both the element to the left of it and the element to the right of it. And so if I do something like 4 plus 5 plus 6, right, I'm going to get their sum. But in Julia, these infix operators are actually derived from functions. And in this case, plus is a function, and I can put 4, 5, and 6 as arguments to the function, and it'll work exactly the same way. Similarly, if I think about a composition of functions like this, so let's say I have 5, I want to take the square root, then I want to exponentiate it, and then I want to take the sine. I don't know why, but suppose that's what I want to do. Then this is equivalent to composing a function that is, first you do square root, then exponential, then sine. So we're stringing these two functions or operators together. And if I use this circular composition operator in Julia, then I can chain these functions together, and this object right here on its own is a perfectly valid and usable Julia function. And then I can call that on 5 or whatever number I'm interested in, and I should get the exact same result. A good thing to note here is this circle operator is a Unicode character. It's probably not on your keyboard, but if you're using Jupyter Lab, then you can actually type this by using the LaTeX tab completion feature. So if I type a backslash and then CIRC, then this is the LaTeX code in math mode for this center circle. And if I type backslash CIRC and then the tab key, then it should turn into that circle. So that's how you can type this in the Jupyter ecosystem with Julia. Just like this plus infix operator is derived from the plus function in Julia, this function composition infix operator is actually derived from a function composition function. And so this should also be equivalent to what I just did. And indeed, we got the same result. So now let's think about what we are actually trying to do. What we're trying to do is we're trying to compose price update with price update with price update we want to do that 100 times, right? So if I use the fill function, I can create a vector that has price update just repeated however many times I asked for. And if I splat out this vector, which in this case I'll fill with 100 references to the price update function, then right here what I've created is a composed function that performs 100 price updates. And if I call that on P0, then in one line I can perform the same equilibrium calculation that I did above. That's pretty cool, right? If you go look on Julia forums, you will see that in very numerically intensive situations, you're often encouraged to avoid this splatting operation. So I will stick with the original equilibrium function from above, but you should know that this can be a very handy syntax and a very kind of legible syntax in certain situations, and also that the compiler just keeps getting better and better. And in this situation, I actually did not see a very substantial performance improvement from using the for loop instead of this splat. So this was another way to calculate the equilibrium, and if we double check, we should have the same values here as we did before, and indeed they seem to agree. All right, now that we know how to calculate the equilibrium, let's see what happens if we increase the number of goods in our market. So when n, the number of resources we're thinking about, increases, then the cost of computing the equilibrium obviously is going to have to increase the computational cost. But this happens for three reasons. The first is that the demand function itself takes longer to compute. So if you take a look at how we designed our demand function above, that function requires multiplying a matrix by the price vector. So the larger the price vector and the larger the matrix, the more operations are involved in that calculation. The other thing that takes longer is computing the price update, which you will recall includes a normalization step. So we have to sum up all the entries of P, and that will also incur a computational cost that depends on n. And finally, when there are more goods in the market, then it basically becomes a little more complicated, and that means that it takes more tâtonnement iterations to find a fixed point or an equilibrium of this economy. Nonetheless, we can still do quite large markets using this code, and this is where Julia's computational performance really starts to shine. So what I've done here is recreated the market from above, but instead we're going to have 800 resources. We're going to create our A matrix, just like above, with one small tweak that ensures that this matrix is well conditioned. So we need actually a stronger negative diagonal on this A matrix than we did before. And other than that, we're just going to set up our supplies and our initial price vector, and we'll use our for loop based equilibrium code from before to compute an equilibrium p bar. Now let's watch closely and see how long it takes to perform this calculation. And one thing I can actually use is Julia's time macro here. So I type @time, and this is going to do this calculation just like normal, but it's also going to show me how long it took. Let's give it a shot. Okay, that was quite quick, right? In less than 1 second, it was able to do 1,000 iterations of tâtonnement in a market involving 800 goods. So I'm pretty impressed by that. Of course, we should double check that this p bar is in fact an equilibrium. So just like before, before we had p bar is approximately equal to price update. In this instance, I've used the slightly more verbose isapprox function. And the reason I did that is so that I could relax my tolerance to this value, which is 10 to the -8th. This is still a pretty tight tolerance, right? We're requiring that the first 7 digits of p bar agree with the next, with the first 7 digits of those in the price update after the decimal. And sure enough, we got a true response here. However, we should also do as a double check to make sure that this p bar is in fact an equilibrium. We can take a look at our excess demand at this p bar. And so if I go ahead and calculate the demand of p bar minus the supply, I will see that in almost all cases, it's quite close to 0, with the exception of a few instances where it is negative. And so here, this would mean that we had a little bit of excess supply. So we will assume that P bar is going to be 0 on that resource. And in fact, we can double check that by replacing this with P bar. And so we are expecting to see a 0 right here. Let's see what happens. Yeah, and we got the 0. So we know that we did this calculation correctly. Good for us. Finally, something we can do for fun is create a histogram of our prices. So let's see how they were distributed. And sort of a fun stochastic project. I'm not sure if it would be possible to prove this in an easy way, but I've noticed that in this particular market design, as the number of goods tends to be increases, then you tend to get pretty much a uniform distribution of the equilibrium prices. So I'm not sure why that is, or if there's a more rigorous way to prove that, but perhaps some more computations and theoretical exploration are in order. Thanks again for taking the time to watch this video. If you have any questions or suggestions for future tutorials, I'd be happy to read your comments. And I've provided a brief list of some further reading recommendations for those who are interested in delving more into this area of microeconomics. These first 3 links all will take you to Wikipedia articles on topics related to those discussed in these 2 videos. And I will say that I was a little disappointed in the depth of coverage in Wikipedia on these subjects. It's not that the quality is bad, they're great articles, but they're just a little more brief than I've come to expect from Wikipedia. So hopefully by the time you're reading this, there's going to be a little bit more material there. I've also provided some academic references that helped me a lot as I learned this, but be aware that you will have to surmount a paywall in order to access these materials.